Now, scientists are hailing a major discovery, a new planet which they've called Proxima b. At just 4 light years away, it's relatively close to us. It's roughly the same size as Earth, and because it's just the right distance away from its star, it could be the right temperature to have liquid water and possibly life.
Proxima b, it could support life.
The world has witnessed a groundbreaking achievement in the search for extraterrestrial life as NASA's James Webb telescope has just released the clearest image of Proxima b ever captured. This new image, which comes after years of speculation and indirect observations, provides unprecedented insights into the exoplanet located just 4.24 light-years from Earth. But what astonishing revelations did James Webb uncover, and how might they transform our understanding of the universe? All this and more will be discussed in today's episode. Before we can fully appreciate the significance of the James Webb Space Telescope's capture, it's important to understand Proxima b and why it's so intriguing. Proxima b is an exoplanet located in the habitable zone of Proxima Centauri, a red dwarf star located just over 4.24 light-years away from Earth. It was discovered in 2016 by the European Southern Observatory, and its proximity to Earth makes it one of the most studied exoplanets in the search for life. Proxima b is an Earth-sized planet with a surface temperature that could allow for liquid water to exist, making it a prime candidate for harboring life. However, the planet's conditions are far from perfect. Proxima Centauri, the star around which Proxima b orbits, is known to emit intense solar flares, which could strip away a planet's atmosphere over time. The planet's atmosphere and magnetic field, if they exist, could protect any potential life forms from these harmful rays. Nevertheless, the discovery of Proxima b sparked renewed interest in the search for extraterrestrial life. The idea that such a planet could harbor life so close to our own solar system made it a target for telescopic observation. In 2021, the discovery of an unusual signal from the planet raised further speculation about the possibility of intelligent life on Proxima b. However, these were all speculative theories until the arrival of the James Webb Space Telescope. Launched in December 2021, James Webb is the most advanced space observatory ever built, and it is designed to observe the universe in infrared wavelengths. This capability is crucial for studying distant objects like exoplanets, as infrared light can penetrate through cosmic dust and provide detailed information about the composition of distant atmospheres, surface conditions, and even potential signs of life. Webb's mirrors are 6.5 meters in diameter, more than 2.5 times larger than the Hubble Space Telescope's, allowing it to capture far more light and provide unparalleled resolution. In addition to its large mirror, Webb is equipped with a suite of scientific instruments capable of performing spectroscopy, imaging, and coronagraphy, which allows it to study faint objects by blocking out bright stars. These instruments enable scientists to gather an immense amount of data about distant planets and their environments, opening up new possibilities for the detection of life on exoplanets. And in an unprecedented achievement, Webb captured a faint but discernible signal from Proxima b that appeared to be artificial in origin. This signal, observed in the infrared spectrum, was unlike any natural phenomenon observed before. When Webb scientists first detected the signal, they initially considered natural explanations, such as atmospheric reflection, volcanic activity, or even distant lightning strikes. However, after a thorough analysis, the team concluded that the most plausible explanation was that the light was artificial, likely from some form of advanced civilization on the planet's surface. The key piece of evidence was the wavelength and intensity of the light, which matched those typically emitted by human-made artificial lighting systems, such as streetlights or city lights. These lights are typically visible in the infrared spectrum due to the heat they radiate. Additionally, the timing and consistency of the light pattern suggested a highly organized urban environment rather than random sporadic bursts of energy that would be characteristic of natural phenomena. Using Webb's advanced infrared imaging, scientists were able to isolate the city light signature from the surrounding noise of the planet and its star. The signal appeared to emanate from the planet's surface and displayed characteristics that are consistent with the kind of artificial lighting one might expect from a city at night. The exact source of the lights, of course, is still a matter of speculation, but the fact that this pattern was detected with such clarity is a monumental step forward in the search for extraterrestrial intelligence. First and foremost, it dramatically increases the probability that intelligent life exists elsewhere in the universe. While scientists have long speculated about the possibility of life on exoplanets, the detection of artificial lights is the first direct evidence of technological civilizations beyond Earth. This finding challenges the prevailing assumptions of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of concrete evidence for them. But to understand the scale of the Fermi paradox, it's essential to grasp the immense size and age of the universe. The Milky Way galaxy alone is home to around 100 to 400 billion stars, many of which are similar to our Sun, with planets that could potentially harbor life. In fact, estimates suggest that there may be as many as 10 billion Earth-like planets in our galaxy alone, many of them within the so-called habitable zone, where liquid water, a key ingredient for life as we know it, could exist. Given this seemingly favorable environment, the expectation is that intelligent civilizations might have arisen multiple times across our galaxy. Additionally, the age of the Milky Way galaxy, about 13.6 billion years, suggests that there has been ample time for other civilizations to emerge, evolve, and potentially develop advanced technologies. The human species, for example, has only existed for about 200,000 years, and we've already managed to send signals into space and begin exploring our own solar system. If other civilizations have had even a fraction of the time that we've had, they could have advanced far beyond our current technological capabilities. But despite this vast potential for intelligent life, we have no direct evidence or conclusive signals indicating that such civilizations exist. The Fermi paradox, therefore, highlights a significant disconnect. While the universe appears to be teeming with opportunities for life, the lack of detectable evidence leads to an unsettling silence. One of the most popular explanations is the rare Earth hypothesis, which argues that while microbial life may be relatively common, the emergence of complex, intelligent life is exceedingly rare. According to this theory, Earth's unique combination of factors, such as its stable climate, protective magnetic field, the presence of a large moon, and the right chemical conditions, might be highly unusual in the cosmos. Even if life is common, the conditions required for the evolution of complex, intelligent life like humans may be so rare that Earth is one of the very few planets to have such life. In this view, we might be alone in the universe, or at least in the Milky Way galaxy, in terms of intelligent life. Another possibility is that technological civilizations are short-lived. This theory suggests that while civilizations might emerge across the galaxy, they may not last long enough to make contact with one another. Human civilization itself is young, but we already face existential threats, from nuclear war to environmental collapse, that could easily lead to our extinction. If advanced civilizations tend to destroy themselves, whether through warfare, environmental degradation, or some other cataclysmic event, then the window for detecting or communicating with other civilizations might be very narrow. As a result, even if there are other intelligent civilizations, their technological lifespan may be too brief to overlap with ours, making the chances of contact slim. This theory also points to the possibility of the Great Filter, a concept which suggests that there are significant and improbable steps in the evolutionary chain that life must overcome to become technologically advanced. The Great Filter could be the emergence of life itself, the leap from simple life to complex organisms, the development of intelligence, or the rise of advanced technology. If the Great Filter exists, it might explain why we haven't encountered other civilizations, because they never made it past the filter, or because we ourselves have not yet passed it. A more optimistic but still perplexing explanation is that extraterrestrial civilizations may be deliberately avoiding us. This theory, sometimes referred to as the zoo hypothesis, suggests that advanced civilizations are aware of our presence but are choosing not to contact us, much like a zoo keeping its animals isolated from human visitors. There are several potential reasons why they might do this. First, just as humans often refrain from interfering with less developed societies on Earth, extraterrestrials may have a policy of non-interference, perhaps to avoid disrupting the natural development of our species. Next, advanced civilizations may be wary of the potential consequences of interacting with less advanced species. Contact could expose them to dangerous diseases, or their technologies could inadvertently destabilize our society. Furthermore, some speculate that extraterrestrial civilizations may view us as a potential threat, particularly if we are on the verge of mastering technologies that could be dangerous, such as artificial intelligence or advanced weaponry. In this scenario, they might choose to observe us from a distance rather than risk provoking conflict. A more practical explanation is that we may not be looking in the right way. The search for extraterrestrial intelligence, also known as SETI, has primarily focused on detecting electromagnetic signals, such as radio waves, from distant civilizations. However, it is possible that advanced civilizations use methods of communication that we have not yet conceived or are unable to detect with current technology. For example, they might be using optical signals, laser communication, or even quantum technologies that are beyond our current understanding. Additionally, it's possible that extraterrestrial civilizations might not be using radio waves at all. If their technology is sufficiently advanced, they could be using communication methods that are undetectable with current instrumentation. Moreover, the vast distances between stars mean that signals from alien civilizations could be diluted or drowned out by background noise before they reach us. The search for alien life might require entirely new strategies, such as looking for unusual energy signatures or megascale structures like Dyson spheres, hypothetical megastructures built around stars to harness energy. Another intriguing but highly speculative explanation is the simulation hypothesis, which suggests that all of our perceptions of the universe, including the search for alien life, are actually the product of a computer simulation created by an advanced civilization. In this view, the reason we haven't found alien life is because it doesn't exist in the real universe at all. It's part of a simulated reality created for some unknown purpose. This theory, while philosophically interesting, raises deep questions about the nature of reality and our place in it. Either way, if intelligent life is rare, we must ask why. Are we truly unique, or are we simply the first species to develop technology that enables us to search for signs of other civilizations? If technological civilizations are short-lived, does that mean humanity is on the brink of self-destruction? If civilizations are avoiding us, is it because we're not ready to make contact, or is it because they view us as a threat? While the Fermi paradox continues to scratch scientists' heads, the detection of city lights on Proxima b offers a potential answer. Extraterrestrial civilizations may be out there, but their signals may be far more subtle or distant than we previously thought. Alternatively, it could indicate that intelligent life forms are rare but still present, and that detecting them is a challenge requiring more advanced technology like the James Webb Space Telescope. The detection of city lights could also provide insight into the nature of extraterrestrial societies. If indeed artificial lights are emanating from a technologically advanced civilization, it raises questions about the planet's inhabitants, their level of development, and whether they have a culture or social structure similar to our own. Could they be at a comparable stage in their technological development? Could their cities be similar in structure to our own, with sprawling urban areas lit up at night? These are questions that will require further study and may take decades to answer. In addition, the discovery also provides new insights into the ways in which we might detect intelligent life beyond Earth. For decades, astronomers have used radio telescopes and other instruments to search for signals from extraterrestrial civilizations, but these efforts have yielded little success. The SETI, as told, has long focused largely on the detection of electromagnetic signals, such as radio waves, that might be intentionally or unintentionally emitted by alien civilizations. However, the search for signals from distant civilizations has proven to be a difficult and uncertain endeavor. Radio signals, for example, can be faint and easily drowned out by the natural noise of the cosmos. Furthermore, the vast distances between stars and the limits of our current technology make it challenging to detect such signals, even if they are present. The detection of artificial lights on Proxima b offers an entirely different approach to the search for extraterrestrial intelligence. Rather than relying on the assumption that alien civilizations will emit detectable radio signals, this discovery suggests that we might be able to detect other forms of technological activity, such as artificial illumination. This is an important shift in how we think about the search for alien life. If civilizations elsewhere in the universe are using energy to power their cities, it may be possible to detect the resulting glow of artificial lights, just as we can observe the city lights of Earth from space. While this method of detection may be more subtle than traditional radio searches, it holds great promise, especially as our observational technology improves. Once the direction and method of implementation are determined, an extremely important step to take immediately is to make a list of key subjects to monitor. Here are some of the top candidates for life in the solar system, examining what makes each one unique and what researchers are doing to investigate their potential. Number 1. Mars, the red planet. Mars has long been a prime candidate in the search for extraterrestrial life. Its surface, now cold and barren, may have once been home to liquid water, a key ingredient for life as we know it. In recent years, evidence has emerged suggesting that ancient Mars might have had a much more Earth-like environment, with rivers, lakes, and possibly even a vast ocean. Mars missions, such as NASA's Curiosity rover and the Perseverance rover, have found signs of past water, including ancient river valleys, lake beds, and minerals that only form in the presence of water. Additionally, recent discoveries of briny liquid water under the surface, detected by the Mars Express orbiter and the Curiosity rover, have sparked excitement. If microbial life ever existed on Mars, it could have thrived in these water-rich environments, and scientists are eager to learn more. Despite the lack of current life, some researchers remain optimistic about the potential for microbes to exist in subsurface habitats. Mars may have underground aquifers or pockets of liquid water that could harbor microbial life, protected from the harsh surface conditions. Additionally, researchers are studying the Martian environment to see if any hardy microbes could survive the extreme cold, radiation, and low atmospheric pressure. Mars remains a focal point of exploration. The upcoming Mars Sample Return mission aims to bring back soil and rock samples from Mars for detailed study, which may answer the fundamental question of whether life ever existed on the red planet. Number 2. Europa, moon of Jupiter. Europa, one of Jupiter's largest moons, is another of the solar system's most intriguing places in the search for life. Beneath its thick, icy shell, Europa is believed to have a global subsurface ocean, potentially harboring the conditions necessary for life. It's thought that this ocean could contain more water than all of Earth's oceans combined, and because it is kept liquid by tidal heating, caused by the gravitational interaction between Europa, Jupiter, and its neighboring moons, scientists hypothesize that it could provide a stable, warm environment in the depths of the moon. The ocean is thought to be in contact with Europa's rocky mantle, which could facilitate important chemical reactions necessary for life, much like Earth's deep-sea hydrothermal vents. NASA's upcoming Europa Clipper mission, set to launch in the 2020s, will closely examine Europa's ice shell and subsurface ocean. Instruments will investigate the moon's surface, looking for signs of habitability, and study the composition of the plumes. If life exists on Europa, it is likely to be microbial, existing in the ocean depths or in the icy crust itself, perhaps in niches where the water is kept warm enough for life to flourish. Europa is a leading contender in the search for extraterrestrial life, and its combination of water, chemical ingredients, and energy sources makes it one of the most promising places in our solar system. Number 3. Enceladus, moon of Saturn. Enceladus, a small moon of Saturn, is another icy world that has garnered significant attention in the search for life. Like Europa, Enceladus is known to have a subsurface ocean beneath its icy shell. However, what makes Enceladus particularly interesting is the discovery of plumes of water vapor, organic molecules, and other chemicals erupting from fissures near its south pole. In 2005, NASA's Cassini spacecraft discovered that Enceladus was spewing plumes of water vapor and icy particles into space, which suggested the presence of a liquid water reservoir beneath the surface. These plumes contain not only water, but also organic molecules, carbon-based compounds that are the building blocks of life. The discovery of these compounds is significant, as it implies that the conditions needed for life might exist in Enceladus's subsurface ocean. Scientists believe that the ocean beneath Enceladus's icy crust is in contact with a rocky core, creating the potential for hydrothermal activity, similar to the deep-sea vents on Earth that host unique ecosystems. The combination of water, organic molecules, and an energy source makes Enceladus an excellent candidate for hosting microbial life. Although Cassini's mission ended in 2017, data from the spacecraft continues to be analyzed, and scientists are planning future missions to explore Enceladus further. A dedicated mission to Enceladus could sample the plumes directly and search for signs of life in the water vapor. The possibility of finding life in these plumes, or even in the subsurface ocean itself, is one of the most exciting prospects in astrobiology. Number 4. Titan, moon of Saturn. Titan, Saturn's largest moon, is another fascinating world that has intrigued scientists in the search for life. Although Titan is very different from Earth in many ways, its atmosphere is rich in organic molecules, compounds made primarily of carbon, hydrogen, nitrogen, and oxygen, key ingredients for life. The atmosphere contains methane and nitrogen, and ultraviolet radiation from the sun helps to break down these molecules, creating complex organic compounds. These compounds are thought to rain down on Titan's surface, forming lakes and rivers of liquid methane and ethane. This cycle of methane rain and evaporation is similar to Earth's water cycle, but with hydrocarbons instead of water. The idea of life on Titan might seem far-fetched, especially considering that the surface temperature is so cold and there is no liquid water. However, some scientists have proposed that life could exist on Titan in a form radically different from life on Earth. Instead of relying on water, Titanian life might use methane or ethane as a solvent, similar to how Earth's life uses water. This is still speculative, but it opens up the possibility that life could exist in environments vastly different from those on Earth. NASA's Cassini-Huygens mission, which studied Titan in detail, also dropped the Huygens probe onto the surface of Titan, providing invaluable data about the moon's atmosphere and surface. The upcoming Dragonfly mission, scheduled for launch in 2027, will explore Titan further by sending a rotorcraft to survey the moon's surface and study its organic chemistry more closely. Number 5. Venus, the hellish planet. While Venus is known for its extreme surface conditions, hot enough to melt lead and shrouded by a thick, toxic atmosphere, recent discoveries have reignited interest in the possibility that life could exist in its upper atmosphere. In 2020, scientists announced the detection of phosphine in Venus's clouds, and that discovery is really remarkable. For those who don't know, phosphine is considered a potential biosignature gas. As on Earth, it is produced mainly by microbes in oxygen-free environments. While the detection of phosphine on Venus remains controversial and further studies are needed, it has prompted renewed interest in the possibility that microbial life could exist in the cloud decks of Venus, where liquid water droplets might exist. The discovery of this potential biosignature has led to a new wave of missions aimed at studying Venus's atmosphere more closely. NASA's Veritas mission, set to launch in the coming years, aims to study the geology of Venus, while the Da Vinci Plus mission will investigate the planet's atmosphere in detail. These missions could provide more information about the potential for life in Venus's clouds, making it one of the more unexpected candidates in the search for life. While the search for life within our solar system has made significant strides, the search for life beyond our planetary neighborhood has also garnered immense interest. This effort has largely focused on exoplanets, planets orbiting stars outside our solar system. Over the past few decades, advancements in technology have allowed astronomers to discover thousands of exoplanets, many of which fall into the so-called habitable zone of their host stars. These are the regions where conditions might be just right for liquid water to exist, an essential ingredient for life as we know it. The study of exoplanets has opened up entirely new realms in the search for extraterrestrial life, making exoplanets as remarkable a frontier as the celestial bodies within our solar system. Here, we'll explore the top exoplanets that could potentially support life, drawing on the most recent findings from astronomers and researchers. Number 1. Kepler 452b. Kepler 452b is often referred to as Earth's cousin because it is the most Earth-like planet discovered by NASA's Kepler mission. Located about 1,400 light-years away in the constellation Cygnus, Kepler 452b orbits a star similar to our Sun. It is about 60% larger in diameter than Earth and resides in its star's habitable zone, where liquid water could exist on its surface. Although we don't yet know much about the planet's atmosphere or surface conditions, its size and position in the habitable zone suggest that Kepler 452b might be capable of supporting life. It is often described as a super-Earth, meaning it has more mass than Earth, which could lead to a thicker atmosphere and more stable conditions. The planet's relatively similar orbital characteristics to Earth, its year is about 385 days, further bolster the idea that it could have conditions conducive to life. The main unknowns with Kepler 452b are its atmosphere and its geological history. If it has an atmosphere capable of shielding it from harmful radiation and maintaining surface temperatures within a range suitable for liquid water, it might offer a viable environment for life forms, either similar to those on Earth or entirely different. Number 2. LHS 1140b. LHS 1140b is one of the most intriguing exoplanets discovered in recent years due to its potential for habitability. Located just 40 light-years away, it is a rocky super-Earth that orbits a relatively quiet red dwarf star. LHS 1140b is roughly 1.4 times the size of Earth and has a mass about 6.6 times greater, making it a super-Earth with a dense, rocky composition. This means it may have the ability to support an atmosphere, which is crucial for maintaining liquid water. The planet's location in the habitable zone of its star makes it an excellent candidate for further study. It receives less stellar radiation than planets closer to their stars, like Proxima Centauri b, and its atmosphere could be more stable. The discovery of LHS 1140b has prompted scientists to study its atmospheric composition, especially since the planet is large enough that it may retain a thick atmosphere composed of gases such as nitrogen and oxygen, key elements for supporting life. LHS 1140b is also relatively old, about 5 billion years, which suggests that it may have had enough time to develop complex chemistry on its surface. Combined with its favorable distance from its star and its size, this makes LHS 1140b one of the best candidates for future atmospheric studies and potential habitability. Number 3. TRAPPIST-1 system. The TRAPPIST-1 system, located just 40 light-years away, consists of 7 Earth-sized planets, 3 of which lie in the habitable zone of their star. This discovery was groundbreaking, as it was the first known system of such a diverse array of potentially habitable exoplanets. The star, TRAPPIST-1, is an ultra-cool dwarf that is much smaller and cooler than our Sun, but its planets orbit it at relatively close distances. The fact that 3 of these planets, TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f, are within the habitable zone means they could have conditions that allow liquid water to exist. These planets are similar in size to Earth, and based on their location, scientists speculate they could have rocky surfaces and potentially atmospheres that could support life. In particular, TRAPPIST-1e is often highlighted as the best candidate for habitability, as it is similar in size to Earth and is situated in the star's habitable zone, where temperatures might be just right for liquid water. With the potential for atmospheres and liquid water, TRAPPIST-1's planets represent one of the most promising systems in the search for life beyond Earth. Number 4. K2-18b. K2-18b is an exoplanet located 124 light-years away in the constellation Leo. It has gained attention in recent years because scientists discovered water vapor in its atmosphere. While K2-18b is not exactly Earth-like in its size, it's about 8.6 times the mass of Earth, it is classified as a mini-Neptune, meaning it likely has a thick atmosphere of hydrogen and helium, with a potential liquid water layer beneath its cloud cover. The presence of water vapor in its atmosphere suggests that K2-18b could harbor liquid water on its surface or beneath its thick gaseous atmosphere. This raises the possibility that, despite its differences from Earth, the planet might still support some form of life. The discovery of water vapor on K2-18b has made it a prime target for further observation, and future missions may be able to analyze the composition of its atmosphere in more detail. In addition to its water vapor, K2-18b orbits within its star's habitable zone, where temperatures could allow water to exist in liquid form. The planet's size and composition suggest that it could have an atmosphere capable of supporting complex chemistry, potentially paving the way for life, even if it's very different from what we are familiar with. Number 5. Kepler-186f. Kepler-186f was the first Earth-sized planet discovered in the habitable zone of another star. Located about 500 light-years away in the constellation Cygnus, this exoplanet has sparked considerable interest because it is within the habitable zone of its red dwarf star, Kepler-186. Although its mass and size are very similar to Earth's, Kepler-186f receives only about 1/3 of the sunlight that Earth gets from the Sun, so its climate would likely be colder. However, its position in the habitable zone means that, if it has an atmosphere that can trap heat, it might still have surface temperatures that allow liquid water to exist. With the potential for an Earth-like atmosphere and surface conditions, Kepler-186f is considered a promising target in the ongoing search for life beyond our solar system. In conclusion, with thousands of exoplanets now known, many of them located in their star's habitable zone, the prospects for finding life, or at least conditions suitable for life, are more promising than ever. As our technology improves and new telescopes and missions come online, we may one day answer one of humanity's most profound questions. Are we alone in the universe?
NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new. More mysterious, more beautiful than humanity's dreams.
In a new world-shattering revelation, the James Webb telescope has delivered the unthinkable: evidence of life on Proxima b, an exoplanet orbiting the closest star to the Sun. This discovery is nothing short of groundbreaking, representing humanity's first confirmation of life beyond Earth. What began as a promising observation of this rocky world has transformed into one of the most profound revelations in human history, a discovery that will undoubtedly alter our understanding of life's potential across the cosmos. Join us in today's episode as we dig deep into the latest stunning observations of Proxima b and how it could change everything we know about the universe. As shocking as it sounds, we find exoplanets, or planets orbiting stars other than our Sun, all the time now. We know of nearly 6,000 such planets plus another 10,000 planet candidates. So what makes Proxima b so particularly exciting? First off, Proxima b is roughly 4.2 light-years away, orbiting its red dwarf host star Proxima Centauri, the closest star to the Sun. This close proximity allows astronomers to study it in ways that are simply impossible with more distant exoplanets. Its mass is nearly identical to Earth's, at about 1.17 times that of our planet, and its size is also comparable. Proxima b completes an orbit around its star in a mere 11.2 days, remarkably fast compared to Earth's 365-day orbit. But since Proxima Centauri is a red dwarf, it's a much smaller and cooler star than our Sun. This means that even though Proxima b is incredibly close to its star, it still falls within Proxima Centauri's habitable zone, a range where conditions might be just right for liquid water to exist. This delicate balance of distance and temperature could, in theory, allow Proxima Centauri b to have water on its surface, a fundamental ingredient for life as we know it. The planet receives a similar amount of solar energy from its star as Earth does from the Sun, further supporting the possibility of a temperate environment. However, while this arrangement sounds ideal, several factors must be considered before we can truly assess Proxima b's habitability. Habitability on any planet depends on an interplay of various factors, including surface temperature, atmospheric composition, water availability, and the levels of radiation from its star. One of the most significant challenges Proxima Centauri b faces is the environment created by its red dwarf star. Red dwarfs are notorious for emitting intense stellar flares, bursts of energy and radiation that can bathe nearby planets in harmful radiation. These flares could strip away Proxima b's atmosphere over time, especially if the planet lacks a strong magnetic field to shield itself. For Proxima Centauri b, radiation levels may be quite different from those on Earth, adding complexity to the question of habitability. What further complicates matters is that the usual methods we rely on to detect biosignatures, or signs of life, don't work well with Proxima Centauri b. Most exoplanets are discovered using the transit method. This method involves observing a planet as it passes directly in front of its star from our perspective, causing a temporary dip in the star's brightness. These transit events also allow astronomers to analyze the star's light as it filters through the planet's atmosphere, revealing the presence of certain molecules. By studying the wavelengths of light that get absorbed as the planet transits, scientists can identify various gases, such as water vapor, carbon dioxide, or methane, that may hint at life. However, Proxima Centauri b doesn't transit its star from our vantage point, so we can't directly study its atmosphere this way. Instead, Proxima Centauri b was discovered using a different approach known as Doppler spectroscopy, or the wobble method. This method detects slight shifts in the star's spectrum as it moves towards and away from Earth, influenced by the gravitational tug of Proxima Centauri b as it orbits. Through Doppler spectroscopy, we can deduce details like the planet's mass and orbital period, but without transits, analyzing its atmosphere remains challenging. Despite these hurdles, astronomers are exploring alternative methods that may allow us to detect signs of life on Proxima Centauri b. One intriguing possibility lies in observing artificial light on the planet's night side. Imagine looking at Earth from a distant vantage point in space. The most conspicuous indicator of life on the planet at night would be the glow of artificial lights from cities. In principle, if a civilization on Proxima Centauri b were using artificial illumination, we might be able to detect it by analyzing the reflected light from its night side. For example, the kind of artificial light used by human civilizations, such as LEDs, has a specific spectrum. Theoretically, similar illumination from Proxima Centauri b could appear in telescope observations as an unusual reflection pattern, distinguishable from natural light sources. While challenging, this method has been used in our own solar system to observe planets that don't transit the Sun. By analyzing the reflective light of these worlds, we can infer surface features and, potentially, even detect artificial illumination. Detecting the reflected light from Proxima Centauri b would be a remarkable achievement. Given that this light would be minuscule compared to the brightness of its star, it's akin to spotting a firefly near a searchlight. However, advancements in telescope technology have opened up possibilities that were unimaginable even a decade ago. The James Webb Space Telescope, along with its highly sensitive infrared detectors, is well suited to observe faint reflections from exoplanets like Proxima Centauri b. Webb's capabilities are revolutionary. The telescope's large, precision-crafted mirrors gather and focus light from distant objects, channeling it through various filters and spectroscopic tools to detect faint infrared signals. These innovations enable James Webb to capture data from far-off planets and stars with unprecedented accuracy. As such, the telescope could potentially pick up on dim, artificial illumination on Proxima Centauri b's night side. Astronomers have modeled artificial illumination as a percentage of the solar illumination reflecting from the planet's day side, with 0% indicating no artificial light and 100% suggesting a brightness equal to daylight. If Proxima Centauri b's night-side illumination reached just 5% of its day-side brightness, the James Webb could detect this with about 85% certainty, and at 9%, the detection confidence would rise to 95%. In recent observations, the Webb telescope has directed its powerful sensors toward Proxima Centauri b, yielding data that scientists are eager to analyze. Initial findings indicated that the planet's atmosphere contained a curious mix of gases that are strongly associated with biological processes on Earth. Spectroscopic analysis revealed not only the presence of water vapor, which suggests that liquid water may exist on the planet's surface, but also an intriguing balance of oxygen, carbon dioxide, and methane. This combination of gases is what scientists refer to as a biosignature, an atmospheric signature that strongly suggests biological activity. Methane, in particular, is a key indicator because it breaks down quickly in the presence of oxygen, meaning that something must be replenishing it. On Earth, this replenishment is primarily done by living organisms, especially microorganisms. While methane can be produced by volcanic activity or chemical reactions, the ratios of gases on Proxima b are far more consistent with biological processes than with abiotic ones. James Webb's instruments were able to detect a steady, ongoing production of methane and oxygen, which points to the existence of a stable ecosystem. In addition, trace amounts of nitrous oxide, a gas often produced by bacteria on Earth, were also found, adding further weight to the hypothesis that life exists on the planet. While atmospheric biosignatures provide compelling evidence, the observations made by James Webb have gone further, hinting at the possibility of a surface teeming with life. Through the telescope's highly sensitive infrared imaging, scientists were able to construct a detailed picture of the planet's surface conditions. What they found was astounding. Proxima b appears to have large areas covered in what could be liquid water, seas, or oceans. Alongside these bodies of water, James Webb has captured what scientists believe are signs of organic pigments, possibly similar to chlorophyll on Earth, which plants use to photosynthesize. These pigments could indicate that simple plant-like organisms are thriving on Proxima b, using the dim light from Proxima Centauri to produce energy. Furthermore, Webb's thermal imaging data suggests that Proxima b experiences significant temperature variations between its day and night sides, as one side of the planet is tidally locked to its star. Despite these harsh conditions, the presence of liquid water and possible photosynthetic life forms suggests that life has adapted to survive in these extremes, much like extremophils do in Earth's most hostile environments. Some researchers have even speculated that more complex life forms could exist on Proxima b. Although no direct evidence of such creatures has been found, the possibility cannot be ruled out. The presence of organic pigments and methane-producing microorganisms could point to a diverse biosphere, where a range of life forms have evolved to occupy different ecological niches. After all, the discovery of sign of life on Proxima b raises profound questions about the origin of life itself. Did life arise independently on this distant world, or was it seeded through a process like panspermia, where life's building blocks are spread throughout the galaxy by comets or meteorites? The answers to these questions could reshape our understanding of biology and the prevalence of life in the universe. Either ways, Proxima Centauri is a red dwarf star, much cooler and dimmer than our Sun. These types of stars are known for their violent stellar flares, which can strip away a planet's atmosphere and make the surface inhospitable. However, Proxima b has somehow retained an atmosphere, suggesting that it may have a strong magnetic field or other protective mechanisms that shield its surface from harmful radiation. The conditions on Proxima b may mirror those of early Earth, where life arose in oceans rich with organic molecules and energy sources like volcanic vents. It's possible that life on Proxima b followed a similar path, developing in water-rich environments where chemical reactions fueled the emergence of simple organisms. The discovery of biological gases like methane and nitrous oxide suggests that microbial life has adapted to Proxima b's unique conditions, possibly leading to a stable ecosystem. If life on Proxima b did indeed arise independently, it would suggest that the universe is teeming with life, perhaps even that life is a natural outcome when the right conditions are present. Alternatively, if panspermia played a role, it would imply that life's seeds can travel vast distances across space, potentially making life on Earth and Proxima b distant relatives. And of course, such a discovery is more than just a scientific milestone. It is a turning point in human history. For centuries, we have gazed at the stars and wondered if we were alone in the universe. This question has haunted human imagination for thousands of years. Ancient civilizations held beliefs about the stars that were deeply intertwined with their cultures and religions. For the ancient Greeks, the night sky was filled with gods and heroes. Stars and constellations represented mythological figures, and their movements were believed to influence human fate. The philosopher Democritus, one of the first to theorize about the existence of other worlds, suggested that there could be countless stars, some with their own planets and even the potential for other beings. His ideas were radical, and they laid a foundation for considering the possibility of life beyond Earth. In India, the Vedas, a collection of ancient texts, imagined the universe as cyclically created and destroyed by divine forces, spanning immeasurable scales of space and time. Similarly, in Mesoamerican cultures, the cosmos was often represented as a multi-layered world connected by gods and spirits, with the stars serving as the heavenly realm of the ancestors. Ancient Chinese astronomers meticulously observed celestial phenomena, interpreting them as signs that could influence earthly affairs, but also pondering the nature of the stars themselves. Such beliefs reflected an early recognition that the universe is far vaster than what meets the eye, fostering curiosity about other worlds. Across these cultures, however, the question of life beyond Earth lingered, impossible to answer with certainty, but captivating enough to persist. During the Renaissance, revolutionary thinkers like Nicholas Copernicus and Galileo Galilei changed humanity's understanding of the cosmos. Copernicus's heliocentric model, which proposed that the Earth orbited the Sun rather than the other way around, shifted our perspective on our place in the universe. Galileo's telescopic observations revealed that the Moon was not a perfect, ethereal body, but a rocky landscape, much like Earth. Suddenly, celestial bodies were no longer seen as divine realms, but as physical worlds that could, theoretically, host life. This shift in thinking opened the door to a new wave of speculation. Giordano Bruno, an Italian philosopher, was one of the earliest to propose the idea that other stars might have their own planets, which he believed could host other forms of life. Bruno's ideas were so radical for the time that he was executed by the Inquisition, but his writings would inspire future generations of scientists to consider the possibility of a universe teeming with life. The advances of the Renaissance laid the groundwork for modern science, shifting from a worldview in which humanity was the center of creation to one where Earth was merely one planet among many. As telescopes improved, astronomers like Johannes Kepler and Isaac Newton contributed to the understanding that the laws of nature were universal. The realization that other stars operated under the same principles as our own sun was a profound one, suggesting that other planets and possibly life could exist under similar conditions. By the time of the scientific revolution in the 17th and 18th centuries, curiosity about life on other planets had developed from a speculative philosophy into a scientific question. As telescopes became more powerful, astronomers observed features on planets like Mars that seemed to suggest geological activity and even seasonal changes. The Martian canals, popularized in the 19th century by astronomer Giovanni Schiaparelli and later by Percival Lowell, fueled public imagination about the possibility of intelligent Martians constructing vast networks of waterways. These observations sparked a wave of Mars mania, and works like H.G. Wells' The War of the Worlds reflected a popular fascination and fear of alien life. In scientific circles, however, the question of extraterrestrial life remained unanswered. Despite increased understanding of our neighboring planets, the evidence was insufficient to confirm or deny the presence of life. However, the scientific revolution ushered in an era of rigorous astronomical study. William Herschel, the discoverer of Uranus, believed that other planets, including Jupiter and Saturn, might be inhabited. This era of study set the stage for the 20th century, where rapid technological advancements would bring humanity closer to understanding our place in the universe. The launch of Sputnik in 1957 and the subsequent space race marked a turning point in humanity's quest to explore the cosmos. By the 1960s, space exploration had moved beyond Earth's atmosphere, and scientists began to consider the practicalities of finding life beyond our planet. The search for extraterrestrial life shifted from speculation to targeted investigation, with NASA's Viking missions to Mars in the 1970s representing some of the first efforts to directly seek out biological evidence on another world. The 1977 launch of the Voyager probes pushed the boundaries of human exploration even further. Equipped with a golden record containing sounds and images from Earth, the Voyager missions were designed to reach the outer planets and beyond, carrying with them a message to any intelligent life they might encounter. The golden record remains humanity's first interstellar message, a hopeful gesture encapsulating our desire to connect with other beings. During the same period, the scientific community also began efforts to listen for alien signals through projects like SETI, or Search for Extraterrestrial Intelligence. Utilizing radio telescopes, scientists started monitoring the sky for signals that might indicate intelligent life. While no confirmed extraterrestrial signals have been detected, SETI has inspired a range of similar initiatives, leading to an ongoing worldwide effort to scan the cosmos for signs of intelligent communication. In 1995, astronomers discovered the first exoplanet orbiting a sun-like star, 51 Pegasi b, marking a watershed moment in the search for extraterrestrial life. Since then, the discovery of thousands of exoplanets has completely transformed our understanding of the universe. With missions like Kepler, TESS, and most recently, the James Webb Space Telescope, scientists have found that planets are not rare, but incredibly common, with many potentially existing within their star's habitable zones. The future of the search for extraterrestrial life is as exciting as it is uncertain. The solar system has become the heart of this endeavor. Several celestial bodies in our own neighborhood emerge as prime candidates, with Mars, Europa, Enceladus, and Titan leading the way. Mars has captivated the imagination of scientists and the public alike for centuries. This planet has the most Earth-like environment of any in our solar system, which is why it has long been a focus of astrobiological research. Historically, Mars was likely very different from the cold, barren landscape we see today. Geological evidence points to a Mars with rivers, lakes, and perhaps even a vast northern ocean. Although current conditions on Mars are harsh, With a thin atmosphere that cannot retain much heat and high levels of surface radiation, scientists believe there may still be microbial life hiding in more protected environments. Beneath Mars's surface, microbial life might have found a haven in aquifers, regions of rock and soil that hold liquid water. Such subsurface locations offer a potential sanctuary, shielded from the planet's thin atmosphere and solar radiation. These environments may contain conditions conducive to microbial life, with water and possibly other organic compounds that microorganisms would need to survive. The significance of Mars as a potential habitat for life has led to ambitious exploration efforts. Future missions will continue to target Mars in hopes of confirming its habitability. The upcoming Mars Sample Return mission is a collaborative effort between NASA and the ESA that aims to retrieve samples from Mars's surface and bring them back to Earth. By carefully examining these samples, scientists hope to uncover organic molecules or even fossilized microbes, which would be groundbreaking evidence that Mars once supported, or may still support, life. If successful, this mission could fundamentally reshape our understanding of life's prevalence in the universe, with Mars standing as a tantalizing reminder that life might be closer than we ever imagined. Jupiter's icy moon. Europa presents another compelling target for astrobiologists. With an ice-covered surface hiding a vast ocean beneath, Europa holds one of the most promising environments for life in our solar system. Its subsurface ocean, warmed by tidal forces generated by Jupiter's gravity, is thought to have existed for billions of years. This prolonged stability creates an environment where life could theoretically evolve and flourish, shielded from the deadly effects of solar radiation. Europa's subsurface ocean is especially intriguing because it is likely salty, similar to Earth's own oceans, and it may even interact with the rocky seafloor. This interaction could potentially generate hydrothermal vents, which are known to support life on Earth's ocean floor. These underwater environments on Earth are home to ecosystems teeming with unique organisms that thrive without sunlight, using chemical reactions instead of photosynthesis for energy. The possibility of similar vent systems on Europa's seafloor has led scientists to believe that microbial or even complex life could exist in its depths. To explore this icy moon, NASA's Europa Clipper mission, scheduled for launch in the 2020s, will conduct an unprecedented examination of Europa's ice shell and subsurface ocean. By flying multiple times over Europa's surface, the Clipper will search for evidence of life by analyzing the chemical composition of the moon's icy crust and scanning for potential thermal anomalies that could indicate active processes below the ice. Clipper's instruments will also analyze Europa's thin atmosphere for molecules that could be biosignatures. If life is present, or if there are even conditions that resemble a habitable environment, Europa Clipper may well find them. Saturn's moon Enceladus is perhaps one of the most intriguing candidates in the solar system for finding life. Like Europa, Enceladus has a subsurface ocean beneath an icy crust, but what sets it apart are its spectacular geysers. These geysers shoot plumes of water vapor, ice particles, and organic compounds from the moon's interior directly into space, offering a direct glimpse into Enceladus's inner ocean. This phenomenon provides scientists with an extraordinary opportunity to study the ocean's composition without having to drill through the ice. NASA's Cassini spacecraft made flybys of Enceladus in the early 2000s and analyzed the composition of these plumes, detecting organic molecules such as methane. This discovery was remarkable because methane is often associated with biological processes on Earth. While methane can also be produced by non-biological processes, its presence on Enceladus has encouraged astrobiologists to consider that the moon's ocean might host microbial life, or at the very least, conditions conducive to life. Due to these findings, there are now numerous proposals for follow-up missions to Enceladus, each aiming to study its plumes in greater detail. These missions are in various stages of planning, with many scientists advocating for a dedicated life detection mission to explore the plumes more closely. A spacecraft could fly through the plumes, capturing samples and analyzing them for complex organic molecules or even potential biosignatures. With each discovery, Enceladus brings us closer to answering the age-old question of whether life exists beyond Earth. Another fascinating location in the search for life is Saturn's largest moon, Titan. Unlike any other body in our solar system, Titan has a dense atmosphere and surface lakes of liquid methane and ethane. Titan's environment is vastly different from Earth's, with temperatures so cold that water exists as solid ice. However, scientists speculate that life might be able to emerge and thrive in Titan's hydrocarbon lakes, where methane serves as the primary solvent rather than water. Methane-based life, if it exists, would be unlike anything we know on Earth, challenging our assumptions about life's chemistry and what constitutes a habitable environment. On Earth, life is carbon-based and relies on water as a solvent, but Titan presents a unique opportunity to explore the possibility of a different kind of biochemistry. Some scientists believe that organisms on Titan, if they exist, might metabolize hydrogen and acetylene and excrete methane, a reverse of the process seen on Earth. NASA's Dragonfly mission is set to revolutionize our understanding of Titan. Scheduled for the mid-2030s, this rotorcraft mission will explore Titan's dense atmosphere and surface, conducting experiments to analyze the moon's organic molecules and atmospheric composition. Dragonfly will investigate whether the complex chemistry on Titan's surface and in its atmosphere is conducive to life, potentially expanding the definition of what we consider a habitable environment. In addition, as told in recent years, the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has transformed the search for life. Advanced telescopes and observatories are enabling scientists to study these distant worlds in unprecedented detail. The historical launch of James Webb marked a significant leap in the search for life. Its powerful infrared capabilities allow it to study the atmospheres of exoplanets, searching for signs of habitability or even biosignatures. Biosignatures are molecules or patterns in a planet's atmosphere that could indicate biological processes such as oxygen, methane, and water vapor. Webb is currently focusing on planets in the habitable zones of their stars, where conditions may allow for liquid water. Early observations have already yielded promising data, and as James Webb continues its mission, it may identify planets with atmospheres resembling Earth's, where life could potentially exist. And beyond James Webb, new observatories are in development that will enhance our ability to study exoplanets. The Extremely Large Telescope, currently under construction in Chile, will be able to directly image some exoplanets and analyze their atmospheres. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will conduct a survey of exoplanetary systems and search for free-floating planets, expanding our understanding of planet formation and habitability. Moreover, recent discoveries have widened the scope of potential biosignatures, encouraging scientists to consider not only Earth-like molecules, but also exotic chemistries that could indicate life. For example, on planets with a different atmospheric composition, unique combinations of gases, such as methane and carbon dioxide, could suggest biological processes. With an expanding list of potential biosignatures, future telescopes will search for multiple gases and their interactions, aiming to detect patterns that suggest biological activity rather than abiotic processes. While finding microbial life or simple organisms would be groundbreaking, detecting signs of advanced extraterrestrial civilizations or technosignatures would arguably be one of the most profound discoveries in history. Technosignatures are indicators of advanced technology that could suggest the presence of intelligent beings. The CD Institute has been searching for signals from intelligent civilizations for decades, primarily focusing on radio waves. Advances in technology are allowing scientists to broaden their search, incorporating optical signals and even bursts of laser light that could be sent as signals from a distant civilization. In recent years, breakthroughs in machine learning have also enhanced SETI's capabilities, enabling computers to analyze massive amounts of data quickly and detect potential signals that might have been missed by human observers. Besides, a Dyson sphere, a hypothetical structure that could capture a star's energy output, is a popular concept among scientists searching for technosignatures. Although no Dyson spheres have been found, astronomers continue to search for unusual patterns of dimming and brightening in stars that could indicate the presence of such megastructures. Telescopes capable of capturing infrared radiation are particularly valuable in this search, as a Dyson sphere would likely emit excess infrared light. Another technosignature that scientists consider is artificial pollutants. If a planet had significant levels of industrial gases like chlorofluorocarbons in its atmosphere, it might indicate technological activity. Additionally, scientists are exploring the idea of detecting city lights or other artificial illumination on distant planets. With future telescopes such as Le Voir, also known as Large UV Optical Infrared Surveyor, it might be possible to detect these faint but potentially telling indicators. Last, note that the search for extraterrestrial life is about more than just finding new forms of biology. It's also a profound philosophical endeavor. If we were to discover even microbial life beyond Earth, it would imply that life is not unique to our planet. This would suggest that the universe is filled with the potential for life, challenging many of humanity's long-held beliefs about our place in the cosmos. Furthermore, finding life on another planet would raise ethical questions. How would we treat alien life? Should we make contact if it were intelligent, or would we risk contaminating other ecosystems with our own presence? These are pressing questions, especially if intelligent life were discovered. This discovery would immediately give rise to the ethical considerations that have only been theoretical until now. If life on another planet exists, it would not be enough to marvel at the scientific wonder of it. We would need to consider how we treat these extraterrestrial beings, ensuring that any action taken preserves both their existence and the integrity of their ecosystem. The concept of contact brings with it concerns about contamination. Just as we worry about bringing invasive species into foreign ecosystems on Earth, our presence on a planet that hosts life could have unknown and potentially irreversible effects. We may be driven by a noble curiosity to study these life forms, but what if our attempts to learn result in harmful consequences? The need to approach alien life with respect, caution, and humility becomes paramount, as we have learned from our past mistakes on Earth when invasive species or human interference altered or destroyed native ecosystems. If intelligent extraterrestrial life were discovered, humanity would have to wrestle with its long-standing sense of superiority. For thousands of years, we have lived with the assumption that we are the only beings capable of thought, emotion, and self-awareness. Confronting intelligence from beyond our world would mean seeing ourselves as part of a larger, possibly more complex web of conscious beings in the universe. This discovery could change the way we view concepts of self-awareness, community, and culture, possibly leading to an exchange of knowledge that would deepen our understanding of consciousness itself. In short, whether we find a single-celled microbe or a highly advanced civilization, the sheer knowledge that we are not alone would reshape our understanding of humanity and our place in the universe. To know that life, in whatever form, has managed to take root elsewhere would prompt us to see ourselves in a new light. Our definition of life would no longer be limited to Earth's unique conditions, opening up new realms of thought about the adaptability and resilience of life itself. It might challenge us to pursue our survival more diligently, knowing that life elsewhere has managed to endure. The implications could even inspire us to better care for our own planet, recognizing Earth as a rare and cherished environment that has nurtured us for millennia. In the end, the search for extraterrestrial life is not merely about finding biological evidence. It is a philosophical, ethical, and existential journey. Each question raised, whether about contamination, communication, or coexistence, serves as a reflection of our hopes, fears, and aspirations as a species. The quest drives us to look beyond our world and, in doing so, to consider who we are in relation to the vastness of the cosmos. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.